Hi folks, this is Declan McCabe from St. Michael's College Biology Department. I am recording this from my shed to practice social distancing in the time of coronavirus. And since I suspect that maybe you've seen enough of the shed already, let's get a better view here. There we go. Now I'm at St. Michael's College. How does that look? So I want to talk about coronavirus and more importantly, how we can reduce the spread of coronavirus by taking some simple precautions. And also I want to show you how to model the growth of coronavirus spread using the simple math that you would learn in our general biology class. So let's see if I can get slides to come up here. Magic, look at that. I can move myself around so I don't block them. There we go. So we're going to talk about how exponential growth works and how that can be used to model the coronavirus spread. So here we go. See if we can make the slides advance. There we go. So in this case, math plus science can actually save lives. Simple precautions and simple basic knowledge we have. Population growth can help us out. So here come the math. So the math we learn in general biology teaches us how populations grow, and we can use that to model infection numbers. We need two numbers to predict the future of infections. We need the number of people currently infected, and then we need to know the rate of transmission resulting in new cases. These are both numbers that we can get or at least estimate. All right, the science is very simple. Physical isolation and hand washing literally reduce transmission. And if you can do those two things, you reduce the rate of transmission, and you can see how that can have an effect using simple math on the size of this epidemic and how rapidly it advances. So in this case, the science can literally control the rate of transmission. The transmission rate is in our hands, literally, in terms of hand washing, but also in terms of the decisions that we make about social isolation. So how many new cases is the first thing you want to predict? And here come the math. Are you ready? This is simple math. You're going to love it. So N is the number of new cases today. Today is March 23rd. We've got 75 cases. Sorry, not new cases, total cases. So in Vermont, there are 75 cases today. All right, next number we need is R, which is the transmission rate. New cases per infected individual per day. And the way this works is you assume that every infected individual has got some risk of passing this condition on to somebody else. You can estimate how many people this person might infect, and you've got yourself a rate. So let's pretend that an infected person infects 3 other people. If you multiply that by the total number of people infected, you can come up with a total number of new cases in a given day in a place like Vermont. Okay. This notation, dNdt, is just the number of cases per unit time. So you could think about this as cases per day, right? This is a rate of increase in the size of our infected population. There we go. So let's work with Vermont's numbers on this now. N is the number of cases, and we have an estimate. We know, for example, today is 75. That is, we're not testing everybody, so it is an estimate. There are certainly other infected people out there, and we don't know who they are, but we have a number we can work with. All right, or the rate of transmission is more challenging. The reason for that is it varies from place to place. We don't really know accurately what our rate is in Vermont just yet. We will be able to go back and look at it over time once we've got several more days of data. And that will be important to do because that will be a number we want to work on and we want to decrease. And more importantly, R varies from place to place. So some countries have much higher rates of transmission than others. And here's some data to look at. So this is a graph I got from the Times of India. And let's get that out of the way there. So if you look, you can see the way this graph organizes here. We've got on the horizontal axis, the number of days since the 100th case. On the vertical axis, we have the number of cases, cumulative. So it's broken up, 1,000, 10,000, 100,000. This is a log scale. The reason for the log scale is you can put a huge country like China on the graph side by side with a city like Hong Kong and actually have both of them be visible in the same scale. And so it's important to use log scale for that reason. If you look at it also, these dotted lines represent how the graph is divided up. So this is if you double the rate of transmission, double the number of cases every day. This is if you're doubling the number of cases every second day. And this is if you're doubling the number of cases every third day. In Japan, they double the number of cases every week. And in Hong Kong, they're doing exceptionally well, and they're doubling their number of cases only every month. You can see that South Korea has done something remarkable. They've gone from a situation where they're doubling their number of cases every day to a situation where they're doubling the number of cases every third day. That's something we should be learning from the South Koreans. We also should be learning from the Chinese. They've gotten their number of cases, their doubling time down from every second day to every third day. And what are they doing in Japan and Hong Kong? We really should be studying those two locations also. Here's the United States. The important thing about the United States, just like China, from place to place in the United States is going to vary dramatically. You can be quite sure that the transmission rate in Philadelphia, for example, or any large urban city where the population density is high, will be much greater than in a rural environment like Wyoming, for example. I would bet that the transmission rate is quite low. I would expect it to be low also in Vermont, and if it isn't, we should be working on that because we have a low population density, and that's an opportunity right there. So, what else have we got going on here? Looks like my slides have stopped. No, there we go. We want to predict the future, always, right? We want to know if we've got 75 cases today, how many will there be in a week, right? And there's also simple math for that. So, N0 is the number that we have today on March 23rd, which is 75. Question is, what is N7, 7 days from now? What's it going to look like in a week? There's the formula for that. NT is equal to N0 times E, which is the base of the natural log, times R, which is that rate I talked about, and T, which is simply time, which will be 7 in this case. You can plug in 2.72 as your base of the natural log. If you're going to plug this in and figure it out on a calculator, you can also use the EXP function in your calculator if you're into that sort of thing. So let's assume a doubling time of 2 days. That roughly gives us an R value of 0.35. I'm not going to explain the math deriving that, but it's fairly simple. N7 then is going to be 75 times 2.72 to the power of 0.35 times 7, which gets you to 603. If you have gone and done this using the EXP function, you'll get a number of 588 or something closer to that. It doesn't really matter. And you might wonder why I don't care about the difference between 588 and 603. It's because this is a model, and the model has its limitations. You know, it's ecological science. We're not going to get precisely at a good number. There's probably some number that'll be better, and a week from now, you can tell me what that number is. So, if we have a doubling time of 2 days, we can plot the graph like this. Here's a number of positive cases. Here's days on the horizontal axis. And you can see that we get to 1/6 of the Vermont population, or 100,000, fairly rapidly, about 20 days, if we have maintained a doubling time of 2 days, okay? If we can push the doubling time down to 3 days, then we have flattened the curve, as people like to say, and we will have reduced the transmission rate, and we won't be overwhelming our medical facilities. So wash your hands, maintain social physical distance, right? If we go even farther and get our doubling time down to 4 days, which is achievable according to the Japanese and according to the South Koreans, right? Certainly the Japanese are having their doubling time being a week, and the folks in Hong Kong have their doubling time at about a month. So 4 days, you would hope, is something we can accomplish. All right, another way to look at this is to consider the facilities that we have in Vermont, and you could apply this to any location you like. Get your local numbers, folks. Here is the number of hospital beds filled with different doubling rates, and assuming a 10% infection, 10% of those folks infected needing to be hospitalized. Why did I choose 10%? I needed to choose something, and I went with 10%. So that may not be an accurate number, but I had to plug something in, so I went with 10%. You could do this yourself in Microsoft Excel really easily. Come up with your own graphs. So if we have a 2-day doubling time, we hit about 800 beds filled in a very short order. If we can push it back to 3 days, then we get the hospital beds filled around 20 days. And if we can push it back to 4 days, then we won't be filling our hospital beds. Why is it graphed at 800, you might ask? It's roughly the number of hospital beds in Vermont. Now, some of those beds are already occupied, and hospitals are working diligently to empty them, but we don't want to be in a situation where we might run out of beds. So that would be not ideal, right? So getting the transmission rate down by taking the precautions that everybody's been asking us to take would be a sensible thing to do. Sound fair? So on we go. You might have wondered in your algebra class long ago, would you ever need the math? Turns out you do. And so I'd like to dedicate this little video to all of the pre-health students, the folks who are now nurses and physician's assistants and medical doctors, all of the folks who asked me many, many times, why are you making me take an ecology class? And the reason we wanted to make you take an ecology class is so that you could deal with the numbers in an epidemic like this. I thank all of those folks for their service. I appreciate your bravery and all that you're doing, including our folks at St. Michael's College Rescue right now. Our fire and rescue people are on the forefront of this epidemic. But hopefully the medical professionals among you are using the math and doing the best that we can do. So disclaimers, folks, has to be done, right? I'm simply demonstrating some simple math here, the underpinnings of population growth. It's not necessarily going to be predictive of Vermont's epidemic. I don't for a minute expect that 1/6 of our population is going to be infected. There are many reasons why that won't happen. For one thing, you know, there are people who will never be infected, for example, because they're living in pretty significant isolation. There are, you know, lots of reasons why I don't expect it to get to that level. It hasn't even happened in Italy, for example. I'm an ecologist, not a medical professional. I'm not really giving you medical advice. I suggest you go to the CDC, Vermont Board of Health, for updated guidelines and do that frequently. But still, wash your hands, that never hurts. Maintain physical distance to prevent transmission. And stay safe, folks. I appreciate you listening. And if I can ever figure out how to stop this, I will. So thank you all. Stay safe, wash your hands. How do I exit this thing? Well, there we go. I guess we end the meeting and that'll do it. I'm playing with Zoom, you might have figured out. Seems like it works. I hope you're all staying safe. Thank you, folks.